So let's continue discussion of week 2 on the kinematics. So what we are discussing in kinematics is we are essentially characterizing the deformation of fluid elements. In particularly, today we will be discussing something called the velocity gradient tensor. So when you read the word velocity gradient, means velocity, how is it changing as a function of x, y, z, and how to characterize, of course, to define the velocity gradient tensor, uh, and also how to characterize the nature of deformation. And what do I mean by that? We'll come to it. But note that in kinematics, we are not studying the full fluid dynamics problems. On the other hand, we are trying to characterize the deformation, the change in the volume element, shape element of the fluid on application of an external force, where we are not discussing about the nature or the origin of the forces. Uh, and the aim of having this discussion is uh, b- at a later stage next week, when we incorporate the forces, external forces and boundary conditions, and there could be internal viscous forces as well and pressure gradients as well. So when we incorporate all of that on the fluid element, we know how to understand or characterize the response of the fluid uh, to the flow, or how will the individual fluid elements deform themselves as a function of x, y, and z. So that part will be clear. And when we apply the forces, we know how the full fluid element will be uh, moving, changing, changing velocity vectors as a function of x, y, z, and then we can basically focus on the fluid dynamics, right? So we then don't worry. So then we know how the motion of the paths are going to be, how to characterize it in terms of tensor. And then when you apply a pressure gradient or a viscous gradient or a boundary condition or electric gradients, suppose if fluid was charged, then we know the response. So that's why we had first discussed the kinematics, then we moved to the full description of fluid flow. By the end of today's discussion, what I expect is not only discuss velocity gradient tensor, but also how to break it up into three parts. So depending upon what the three parts are, it can be used. Certain terms, certain parts of the tensor will characterize the volume change in the fluid element if it is a compressible fluid, and some other part will be the deformation tensor, and some other part will be the rotation tensor. So that's the aim of today's discussion, not only to define that, but also how to characterize or break it up into three parts. Okay. So that was the preamble, and to come to the actual point of what we're going to discuss today, step by step. The first was a preamble to the discussion. So basically, suppose at a given time t, you have a velocity field. So you're looking at the entire velocity field at a fixed time, and the velocity v at r1 is suppose here, and you have a different velocity vector. There should be a vector sign here, dash, at r plus dr, right? And suppose this would be the fluid element. Then the change in the velocity field dvi, I being suppose the x component, right? But in general, I could be x, y, z. But let's suppose the x component when I equal to x, then we can talk about how the x component of the velocity is changing in the x direction into dx, how the x component of the velocity is changing in y, and how the x component of the velocity vector is changing in the z direction. And the total dvi will be dvx dx into dx, this into dy, dvx del z into dz. So that's the total change in velocity, right? And this can be written, of course, dvi, suppose I equal to x equal to sum over j del vi del xj into dxj, where j is repeated, which implies that it is a sum. So dvi is this x, this, and this, right? So xj. So in general, I can run from xyz or 1, 2, 3, right? When you're writing a tensor. So just focusing on this del vi del xj, right? Where I can run from 1, 2, 3, and j can run from 1, 2, 3, xyz. Then gij, the velocity gradient tensor, can be written as del vi del xj. In general, gxx del vx del xj del vx del xy. Here you would have del vy del xj, and so on and so forth, right? So basically, so dvi, here you have a repeated index, and we are just focusing on this, and you're writing down the 9 components in a tensor. And the next idea to explore is that any square tensor can be written up as a sum of a symmetric component and an antisymmetric component of the tensor. So basically what you have done is you had del vi del xj, and you added a half to it, del vi del xj, and you del vi del xj here again. So you have written half plus half, and to this you have added del vj del xi, and you have subtracted del vj del xi with a half sign. And if you notice, and if this is the tensor, and if you change j and I, then you would have del vj del xi plus del vi del xj, and you can see that it's a symmetric. And if you have gji, mean, then you would see that this basically is a change sign, right? So you have broken it up into two parts, which is possible for any tensor. Now, this velocity gradient we'll write in terms of the symmetric component E and the antisymmetric component, denoted by omega ij. And they, of course, have different parameters. This will show later in the class that this corresponds to rotation of the fluid element without deformation. When it acts upon a fluid element, it will deform it. It will rotate it without deformation. And let's try to figure out what this does to a fluid element when this velocity gradient tensor acts on a fluid element. So this one can be broken down into a diagonal and an off diagonal part. Okay, so let's focus on only the diagonal terms, and that will be del vx del x, del vy del y, z del vz del z. And for ease of understanding, just imagine that we have a planar flow. We're discussing about a planar fluid element in x and y, and this is 0 for the moment, right? So any deformation, we have only del vx del x and del vy del y. Now suppose there's a fluid element, uh, so this of length dy in the y direction, in the two direction, called y to be 2, and dx in the x direction, right? Now suppose that there is flow. Now there is an external force due to which there's a flow, and for which you can define a velocity gradient tensor, the appropriate velocity gradient tensor corresponding to the externally applied conditions, which we are not discussing. And suppose this fluid element under was subjected to a velocity gradient which had only diagonal terms, and suppose only these two diagonal terms, then after time dt, this element dx would have undergone a change and become dx dash, and dx dash of a different length. So suppose this black thing was there, and now it will become this blue colored box, uh, if there are only diagonal elements. And basically what happens is, just one second, Basically, what happens is that this dx dash is dx plus change of the x component of the velocity in the x direction, because you have only suppose diagonal components, right? uh, into dt, into dx, right? So basically the change will be del v del x into dx, and if you have a larger different values of dx, it would be uh, different amounts of distortion for the same velocity gradient. And if it is acts for a longer time, then you will have a more. So del v del x into dx into dt. And similarly, the y component will be deformed in that you have dy plus del v del y, rate of change of y component of the velocity in the y direction, how it changes in the y direction, del v del y into dy into dt, right? So basically, if you had a box in this black colored, it would become blue, because only along the axis components, x, the principal components, if you like, have they changed. There's a del v x del x, right? And we suppose these terms are zero, non-diagonal terms. So if you talk about relative increase in length, relative will be dy dash into dy, right? Uh, so basically you can calculate, yeah, so that will be the relative increase in length will be del v1 x1 instead of x. I'm writing it in general. So 1, 2, 3 being x, y, z, if you like, but it can be some other x1 dash, x2 dash, x dash, y dash, z dash as well. So del v x1 del x1 into dt. And relative change in the area, now if you multiply dx dash, dy dash, and subtract out the previous area, the relative change in area will be del v1 del x1 plus del v2 del x2 into dt. You can just calculate the new area, subtract out the old area, and divide by dA, right? In 3D, you will have such a term, del v1 del x1 v2, sorry, this has to be del x2 and del v3 del x3 into dt. This is not, so this so if this was the area, this would be the volume in 3 dimensions, and that is equal to the relative change in volume. So delta v by initial v is divergence velocity vector into dt, and that is the relative change in volume, relative, remember, right? So dv by v, if you write, but this is volume, not vector, velocity vector in time dt. And the relative change in volume can be calculated by calculating divergence of v into dt in time dt, that is how much change. And if divergence v was equal to 0, the flow has no volume change. There might be a deformation, but there is no volume change if divergence v equal to 0, which is anyway always true for incompressible fluids. And the other thing to note is that the trace of the matrix is typically independent under rotation of the axis. As a consequence, this result, if divergence v is equal to 0 in some choice of axis, even if you change it, the results and consequences of divergence v equal to 0 will continue to be there for a different choice of axis. So now let's discuss the effect of off-diagonal terms of Eij. Just to remind you, this is the symmetric component Eij, and what are the off-diagonal, how do we interpret a flow field or a velocity gradient tensor which has only off-diagonal terms of Eij. And we'll discuss this with an example after we have finished the theoretical discussion. And suppose there was a fluid element, again, x2 or y, and then dx1 in the x1 direction or the x direction. And suppose this fluid element, you have chosen an axis so that this origin is moving with the same velocity as the velocity of O, so that after time dt, uh, this position hasn't changed, mm, as a consequence of the velocity gradient tensor. So this point is moving, so the origin is moving, origin of the reference frame is moving exactly the velocity of O, so that is always stationary. And the action of the flow characterized by Gij with off-diagonal elements, this fluid element will become, where C would have moved, suppose, to C dash, and suppose this B has moved to B dash, okay, and uh, and this point O remains unchanged. And since we have the off-diagonal components, non-zero off-diagonal components, we can say that B dash or B dash B equal to del V del x2. So how velocity in this V2 direction, in the two direction, is changing as you move along x1. So if you have moved from here to here, the velocity of V2 might be different. So in time dt, the bb dash will be del v2 del x1 into dx1, and if dx1 is smaller, this deformation will be smaller, so it will be some point here, into time dt. And similarly, c dash, because there are off diagonal terms, will be del v1 del x2 into dx2. So basically how this v1 is changing as you move in x2, right? So this is changing as you move along x2, hence this point has moved from here to here. So del v1 del x2 into dx2 into dt, right? Now I've copied, so this part I've copied to the next slide. Now what to discuss is this angle alpha, d alpha, and if d alpha is small, it is equal to tan d alpha, and that is equal to b dash b upon OB, and that is equal to, if you notice, you just divide, and OB is dx1. If you divide by dx1, you get del v2 del x1 into dt. And similarly, cc dash, right? So cc dash by dx2, right? Uh, cc dash cc dash by OC, which is dx2, will be this d beta, which is equal to tan d beta, and that is del v1 del x2. And if you put in the sign, because suppose it has deformed in this way, then d beta will be minus del b del theta, del b del t, right? Uh, yeah. So basically, I'm taking it this side, so change in d beta with time equal to del v1 del x2. And similarly here, if you take the time down, you will get del alpha del t. So basically, bb dash by dx1, that's d alpha, and then you take dt down, rate of change of alpha with time is del v2 del x1, and rate of change of beta angle with time is del v1 del x2, which one just get from the geometry. And then the deformation, which is how does OC, the vectors OC and OB, deform the fluid element, gets deformed into the fluid element with sides OC dash and OB dash, and so on and so forth. So rate of change, uh, right? Why rate of change? Because we remember, I mean, just check the dimensions. So rate of change of the angle between OB and OC, which can be given as d gamma dt, is this. Okay, so this is and this is minus, comes with a minus sign. So d alpha minus d beta in the unit time, the rate of change of angle, and that can be written down as del v2 del x1 plus del v1 del x2, or equal to 2ij, right? Because ij basically comes with this formula but a half in front of it. And if you have just this, then yeah, so you can just check the formula. Thereby, the off diagonal terms of Eij give the local angular deformation rates. The diagonal elements give the relative change in volume, whereas the off diagonal terms give the local angular deformation rates, right? So trace the diagonal term del v1 del x1 and sum over all the three directions. Divergence v was giving the local relative volume deformation rates. Here it is giving angular deformation rates. And just what I said before, that all elements of Eij or Gij have units 1 by tau, and that you can figure out because, yeah, so V has dimensions of L, this has dimensions of L, and what remains is 1 by tau, right? And just to say that this term itself, Eij itself, can be written into a purely diagonal term. Well, so this is your conical delta, and this has basically only 1 1 1 along the diagonal, and you multiplied it by ELL, so you have a 1/3 Dij ELL, right? And you have subtracted out this same term, and now this term is, which you represent by Tij, is a measure of volume dilatation, and whereas this term is completely off diagonal, right? And is off diagonal uh, parts of the symmetric matrix. Sorry. So this part has zero trace. This part has zero trace, so that this does not at all. I mean, if you have finite terms of the so-called deviated Dij, then you don't have volume change at all. So you have broken it down into components which have a volume change, don't have a volume change, have a deformation without volume change, and some other part which we will cover later, which leads to rotation without deformation, right? So depending upon how your shear gradient, velocity gradient matrix is, you can characterize the different kinds of motion or the deformation of the fluid elements. And Dij, this term can of course be written as del v, del v1 del x1, so basically written down all the diagonal terms, right? And writing down the off diagonal terms is of course relatively easy. But what does this mean? It means these kind of terms. So it's just written up, right? So just to summarize, relative volume dilation rates will be basically depending on the way it is defined, divergence V, and so on and so forth. It's 3 times Tij, and the angular deformation rate is 2 times Dij. And this basically does not change the volume at all. Now, what does the antisymmetric component do? The antisymmetric component, as we saw, yeah, here or here, the antisymmetric component is half del vi del xj. If you take I and x, I to be x and j to be y, then the term becomes wxy equal to half del v del vx del y, and this is del x of vy. And this is of course reminiscent of the z component of the curl of v, right? This curl of v will be, yeah, you can just write it down. And so what will show that the z component, suppose, of the curl of v can be written as minus epsilon ijk. So this is the Levi-Civita symbol which we discussed last week, into omega ij, which is this, right? And that will give us the angular comp, the angular aspect, the curl of v, as we'll see with, and will come with a minus sign. So how do we get it? So basically, it will, if this is reminiscent of rotation, so basically the fluid element will rotate like this uh, without deformation. And if you have a velocity gradient, or if you have a force field which creates a velocity gradient tensor, which has only the antisymmetric component, the consequence will be after time dt, without deformation, the fluid element would have rotated, right? So if you identify the look of the velocity gradient tensor, then you know uh, what is happening to the fluid element as external forces or boundary conditions are applied. So just to remind you, Wij is antisymmetric, and how to prove it? Well, Wij uh, equal to minus Wji by definition. And if you just write down the expression for this, if you write down the expression for Wji and come with the minus sign, and then you say this equality is satisfied. So it is an antisymmetric tensor. Now, suppose we choose a velocity gradient tensor Gij, where the symmetric part is 0 and only the antisymmetric part is non-zero, then we know that the Gij also has to be antisymmetric, right? And which means if this is antisymmetric, then del Vi del xj will be equal to minus del Vj del xi, because Gij has only antisymmetric parts, because only this is non-zero and this has been chosen to be 0, and since this is equal to this, it will have only antisymmetric parts, right? But yeah, so Wij, or whatever, omega ij, will be del Vi del xj minus del Vj del xi. Now if you substitute from this, if you substitute this, right, then you substitute this, suppose, then you essentially get these two combined to form minus 2 del Vj del xi, or equivalently you will get uh, 2 del Vi del xj. So that will be the value of Wij, right? Using the antisymmetric property of the flow field, assuming you have only the antisymmetric component of Gij, right? And to show that it basically shows represent deformation. So I plotted the previous graph, and I shall show that del alpha will be equal to del beta and not with a minus sign. So just tan d alpha, just as before, will be d alpha into bb dash into dx1, just the previous result. This, and that is equal to del b2 del x1 in general. And similarly, tan d beta will be equal to d beta, and that will be equal to cc dash into OC. OC being this into this. I mean, the difference between these 2 points. And that was shown to be del V1 del X2, right? And that was minus del B del data. Now, because Gij has only the antisymmetric part, we have also this behavior which is ingrained in the fluid flow property, del Vi del Xj, because that's by definition, because this was the antisymmetric part. And if you substitute, suppose del V1 del X2, right? So this, you substitute this, you will realize. So basically, if you just so in one of these things, if you substitute, either substitute del V2 del X1 in terms of the other one, or substitute this in terms of the other one, you'll see that del alpha del t equal to del beta del t, which means the change of this angle and that angle is exactly the same, which means that if this has moved this much, then del beta would have moved in the same direction, in the same manner, the opposite direction, as a consequence of which we can infer that the role of this fluid element, this GIG tensor, this part of the GIG tensor acting on the fluid element will just rotate the fluid element, right? Just to summarize, and now we will see this GIG tensor with an example in the next class. But just to summarize, the relative volume dilation rate is 3 into Tij. The angular deformation rate is 2 into Dij, and and the so this was the angular deformation rate, and the rotational rate del alpha del t, which can be measured, is basically the minus of the curl of v with a half sign, right? And curl of v is del vx del y minus del vy del x, right? So that's the expression for the curl. But the rate, the rotation rate, is minus the curl of z. Suppose there was only a planar flow, right? And this is, on one hand, this is equal to this, but you know that this is equal to the minus of curl v, and that is what the omega ji is. Or if you want to write in terms of omega ij, this quantity is minus omega ij, or omega ij is minus, if you like, curl of v minus of it, right? So this represents, if these terms are present in the fluid gradient tensor, then it represents that there can be a local solid body like rotation of the fluid element without deformation. We'll discuss an example just in the next class. Hmm.